got a meeting in Marseille, but you live in Paris. You've got a date with your French boyfriend, but you study in Amsterdam. Just a few hours on a high-speed train, and you're there. Ever wonder what it takes to make these massive machines run over 300 kilometers per hour? This. It all comes together in the mega factories of Alstom, makers of Europe's most famous high-speed trains. It's 2 a.m. and Guillaume Reux is hard at work.
Want a coffee? This is one of my most important jobs, to keep everybody awake, to make sure there will be no problem, so coffee is one of the important things. How to make a good Italian coffee. Okay, here it is. This is a secret, huh?
It's been 6 straight months of all-nighters.
Not too bad. Not too bad. Sorry, I got a problem there. I have to go back.
But this young French engineer is no intern. At only 28 years old, Guillaume is in charge of the last stage of testing on a brand new line of high-speed trains. The first ever for his new Italian clients.
Vediamo che cosa possiamo fare. Grazie, ti facciamo sapere.
This make-or-break phase of testing marks the end of a 10-year journey for a truly unique train, made by the company that makes more very high-speed trains than any other. Alstom makes trains for 60 countries worldwide. They make up nearly a fifth of the world's railway market. The French train makers have already reshaped travel in France with their famous line of TGV trains. Now they're trying to repeat the accomplishment in Italy with a redesigned train called the AGV. Meeting the challenge will take years of design and development, months of welding, tooling, fitting and cabling, and thousands of kilometers of test runs. Building the AGV trains happens mainly in 3 French factories. Ornans, where the motors are assembled. Le Creusot, where the bogies or wheeled carriages take shape. And La Rochelle, where the shell is welded and the whole train comes together. But before any trains take to the tracks, they have to take shape. The train makers want to completely reimagine high-speed trains from the inside out. The design team gathers in Paris for a sketch session.
À votre avis, qu'est-ce qu'on peut faire pour réussir à exprimer cette idée d'avion de chasse là? C'est quoi les codes de l'avion de chasse? C'est bon, la vitesse, on l'a bien, mais c'est quoi? C'est la bulle, c'est les lancements, c'est... Je sais pas, Augustin, comment t'exprimes ça?
Jusque-là. Voilà, pour un maximum de visibilité, de lumière à l'intérieur de la cabine.
D'accord,
on pourrait même mettre
à l'intérieur de la cabine.
La trappe pour l'avertisseur. L'avertisseur sonore. Ouais, l'avertisseur sonore.
The design looks great, but it's not all about a pretty picture. The train shell needs to have optimum aerodynamics for efficiency and a quiet ride. To analyze the way wind travels over the ultra-sleek AGV, they perform aerodynamic tests in a wind tunnel for scale models.
The nose is much more elongated than the TGV duplex nose. You see also it's more rounded the roof fairing, which is pretty good for crosswinds.
That's right.
You'll see here
The shape.
bogey fairing,
Right.
which is very good for noise reduction.
On arrive quand même à percevoir cette concavité, cette forme, c'est vraiment intéressant.
Je crois pas qu'on ait déjà vu ça quelque part dans le design ferroviaire.
The extended nose and rounded body keep airflow smooth above the train, and the sloped covers over the front and rear wheels keep air from jostling the train from below.
This is good.
This is much better. Yeah.
Yes.
Meanwhile, teams across France rework the train's other main components. The motors that push the train, the bogies which are the wheel carts that carry it, and the safety systems that keep the passengers alive. For train manufacturers, speed means success, and their competition isn't cars, but aeroplanes.
For the train to be a big competitor for planes, you have to be able to do a distance of 1,000 kilometers in less than 3 hours.
That's France top to bottom, in half the time it takes on the road.
All the tests and all the experiments we made show that when you have a travel time up to 3 hours, you get almost all the passengers. Beyond 3 hours, of course, you still have traffic, but the airplanes come back. At 3 hours travel time, the share of the market for the TGV is something like 70–75%.
The TGV has a top speed of 320 kilometers per hour. That's a touch slower than the target. Alstom wanted to up the top speed for the AGV to 360 kilometers per hour. The secret to kicking up the top speed is all in how the power is distributed. Every high-speed train Alstom has ever made uses the electrical equivalent of a locomotive, called a power car. That's a dedicated train car for the motor, the power equipment, and of course, the driver. But there's a catch in that design. Each train needs 2 power cars, one in the front and one in the back. That's 2 full train cars of equipment where there could be paying passengers. So the designers came up with a revolutionary solution. Take away the power cars. Instead of having power concentrated at each end, it would now be distributed onto undercarriages called bogies, with motors built right in. This way, the train can have seats where the power cars were, adding 100 more passengers, while keeping the same weight. Less wasted space and less wasted energy.
So what you can see here is a 3D model of the AGV power bogie. It's a bogie where you'll find axles, a reductor, a traction motor, suspensions here and here, and a bogie chassis which will bring all these together.
But your average train engine couldn't possibly fit on a bogie, so they had to come up with a whole new motor.
In order to mount a motor on the bogie, you have to reduce its size, and more importantly, its mass.
The new motors had to be 1/3 of the weight of the TGV motors. A lighter motor means more speed. Engineers had to completely rethink train motor design. All high-speed train motors have a fixed shell, called a stator, and a spinning axle in the middle, called a rotor. Electricity and magnetism make the rotor move, which in turn moves the train. But feeding electricity into a rotor has a drawback.
Because whenever a current flows, there are losses, which are called joule losses.
They found an elegant solution, lining the rotor with magnets. Here's how it works. Electricity from the wires above the train is fed into the stator. This creates a magnetic charge. This charge interacts with magnets on the rotor, causing it to spin around the axle. The new design is paying off big time. Each AGV motor puts out 1,200 horsepower. That's twice the muscle of a Dodge Viper. But no one's going anywhere without a power source. High-speed trains get their power from the high-voltage lines running above, through a pantograph. The connection happens through a thin strip of carbon and copper.
There is a pantograph, which is the size of the hand, and when the both are touching together, there is electricity flowing through the train. And just by this little contact, it moves a train of 200 meters long, 400 tons heavy.
The metal conducts electricity well, but is softer than the power lines. So the lines are strung up in a zigzag pattern to keep from wearing grooves into the pantograph.
So in this cable, there is about 25 kilovolts coming from the high voltage line that is on the top of the train and which is distributed to the traction of the train.
That's enough juice to power 36 Ferraris.
The only advantage is that we are not having just 2 passengers at a time. We are about 500 people in the train, so it's a very efficient system.
Guillaume steps into the cabin for a test run.
We are spreading electricity all over the train. We are ready to go.
The train is fired up and the crew are all set. Guillaume and his team have to test under the cover of darkness. The Italian Rail Authority doesn't want dry runs to get in the way of regular train service.
The moment then we arrive, the sun is down, we go to the bed, the sun is down, so you don't realize you are at 300 kilometers per hour. You just are in the tube of metal and it's black all over you, so.
The AGV train is outfitted with sandbags to simulate seats and passenger weight, and water to simulate rainy conditions on the tracks.
So we are testing the train under real condition, just to make sure there will be no surprise at the right moment.
And the engineers have separate lab stations for each major technical category. An electrical station that monitors the pantograph. Master computers that control the train. And traction, which checks the brand new bogies carrying the train. Before the power bogies could make it on the AGV, the train makers had to prove that the new technology worked. Alstom has made a habit over the years of showing off their new designs in a big way by pushing the limits of speed on rails. When the TGV was ready for its first runs in 1981, Alstom and SNCF had to prove it could compete with aeroplanes. So they set out to break the rail speed record.
The different steps in speeding were started in 1981 with the first world record at 380 kilometers per hour. Then in 1990, we settled another record just over 500 kilometers.
That record stood for over a decade. Many thought it would never be broken. Alstom started construction on a prototype using the newly developed AGV motors. They called it the V150, after the target speed of 150 meters per second. The V150 combined 2 TGV power cars with the AGV power bogies. And on April the 3rd, 2007, the V150 surpassed its own name, clocking a top speed of 160 meters per second, or 575 kilometers per hour. The champion train was paraded down the River Seine in Paris for a ceremony at the Eiffel Tower. The #1 safety concern for any train maker is derailment. And Alstom's solution is the strongest link between the AGV and its predecessor, the TGV. Classical train sets place each car on 2 bogies, but Alstom's trains put a single bogie in between every 2 cars. This makes the train set sturdier. If it goes off the rails, the set stays straight and doesn't collapse. It also reduces noise and vibration on board by moving the bogies from under the carriages to in between. But derailments are very rare on high-speed train lines. A more pressing concern is something that happens all the time. High-speed trains pass each other up to 300 times a day. This creates pressures of up to 1 ton per square metre. A weak shell could buckle under the strain, putting lives at risk. The TGV is built with a carbon steel body shell, which is strong, but weighs a lot. Alstom wanted the new AGV to shed a few tons, while keeping structural strength. So they made the switch to an all-aluminium body shell. But no matter what the shell material, a driver running a train at speeds of over 300 kilometers per hour needs more than a bit of protection. So designers developed a safety technology in one of the most crucial areas of the train, the nose. The mega module is basically a supercharged crumple zone.
It's a crash module, which can absorb up to 4.5 megajoules of energy.
That's as much force as TNT.
The mega module is made up of 5 cells, which will absorb energy during a crash through crumpling and deformation of the sheet metal parts.
With all the winning designs in place, the new AGV train is ready for construction. The Alstom factory at Ornans, France, is a plant with a purpose. The entire factory lives for one thing: making the muscle behind high-speed trains. They have an order in for over 200 electromagnetic motors for the new AGV train. The first thing they'll need is a lot of copper. But before these conductive coils can charm their magnetic counterparts, someone has to get them ready for the big date. The fully wrapped coils get fitted into the stator by 2-man teams. It takes choreographed teamwork to pull, place, and mallet the coils into the shell. Now that the stator has been dressed, it's ready to meet its mate, the rotor. But first, the rotor needs its most important accessory, permanent magnets. The magnets arrive in specialized protective boxes and are delivered directly to the white room. Their exact placement on the rotor is a closely guarded secret. Next, the rotor magnets get their own insulated wrap. This time, a machine handles the job. Decked out in its finest metals, the rotor is ready for its date. Here, the fated pair meet for the first time. The whole process takes 6 hours and involves around 50 parts. Quite the complicated first date. Next, the motor heads to a sealed unit to go through a serious spin cycle. A meter outside the unit records the motor's performance as it's sped up to maximum revolutions. It has to get up to 4,000 RPM to withstand the demands of high-speed travel. Another screen registers voltage frequency, which is a stress test for the motor. The fully tested motors are now the high-powered heart of the new AGV, and they're ready to travel down the mountains to join the bogies. These revolutionary bogies are born at Alstom's factory in Le Creusot. Like all structural elements for high-speed trains, it begins with raw metal plates. Every year, Le Creusot uses over 22,000 square meters of sheet metal. That's enough to cover 3.5 football pitches. Each 1.5-ton sheet makes its first stop at the plasma cutter. Robotic chisels then trim the steel like a hot knife through butter, and massive bending units press the plates into shape. It takes some pretty massive machines to handle all this heavy metal, but it's the trained eyes and hands of master welders that put all the pieces together.
As soon as we put the hood on and press the trigger, we get this electric arc. We feel, let's say, that there is no one around anymore. It's you and the weld. No one left around.
It takes the welders 21 hours to assemble each bogie.
It's me who places the metal, not a machine. And that's what I really like. Looking at well-made welds, I appreciate them. Welds need to be top-notch. When we weld, we think of the people who are going to ride this train. The lives of the passengers depend on every weld.
The welding may be done by hand, but the arms that check the welder's work are decidedly robotic. The man behind this machine operates a 3-dimensional sensor robot that scans the bogie.
The machine senses dots And once they've been sensed, we have a console which gives us references. We have to verify if these references are good or not.
The machine sends carefully calibrated arms around the entire frame to analyze every nook and cranny. It's comparing relative distances to the reference data in the blueprint. After clearing the robot test, the AGV bogie is baked in a 600-degree oven for 12 hours. This solidifies the new joints and locks them into place. The fully finished bogie frame is now ready for its key components. This includes all the cabling, suspension, and of course the most important part, the wheels and brakes. This machine applies 120 tons of pressure to secure the wheels to the axle. This is enough to hold them in place forever. And like the 3D sensor at the welding area, a calibrated arm keeps track of required distances. With the wheels secured to the axle, it's time to put on the bogie. It's kind of like fitting the train's feet into a pair of roller skates. If they don't get it just right, this bogie is not going anywhere. Now for the finished bogies to meet their muscle, none too soon. The motors have just arrived from Ornon. Like a heart surgeon performing a transplant, one worker carefully installs the 750-kilo motor and connects it to its major arteries. The newly finished AGV bogies hit the road to meet the rest of the train at the La Rochelle mega factory. On board the mobile lab, the traction team tests out the new bogies. The AGV picks up speed and they move to step one, getting the train up to 300 kilometers per hour. Kilometers per hour. All systems look stable. The train works. But the true test isn't only how fast the train can go, but also how fast it can stop. The AGV mobile lab is running the train through emergency stop scenarios.
In the process of testing the brake, each step is very important because we're dealing with security of the passenger and of the train. So it's a very tough part of the testing session.
And a 400-ton train can't stop on a dime.
On this train, we have two braking systems. One is electrical and the other one is pneumatic. Just in case of emergency, you can use both of them by emergency brakes.
It takes the train 3 kilometers and just over a minute to come to a complete stop. The immense stopping force can cause the brakes to heat up to 600 degrees. That's magma hot.
How is the test going on? Not too bad, actually. Look at the curve. There is no slipping of the... No slipping. Temperature, 364. And the speed was not too bad. It's kind of a good, guys. We did it.
One run down, 4 tests to go.
Another one in the basket.
The AGV bogies arrive at La Rochelle for the final assembly. But the train's skeleton needs to be put together before it's ready for the bogies. The La Rochelle factory has had to completely retrain their welding staff to work with the new aluminium structure. Aluminium needs more prep time than steel, and the welds themselves call for the best hands in the business. It can't be rushed. It takes 60 workers 3 weeks to complete a train set shell. But it's certainly worth the saved weight. The AGV's aluminium shell is 35 tons lighter than previous generations. The completed shell now moves on to the next phase, the paint shop. The Italian clients want a train that will really grab public attention, whether they're standing on the platform or watching it fly by. So they chose a deep race car red for the paint job. The newly welded AGV body shell is moved to the paint shop with the help of a mobile train hanger. Using high-pressure sprayers, they coat the exterior of the AGV with a thin layer of water-based paint. Next up, the crimson coat. Each coat takes over 3,000 strokes, all by hand. Once the shell is painted and has dried, another technician checks the thickness of the paint to guarantee a smooth finish. Using an ultrasound sensor, the technician checks every side of the train to make sure the paint is exactly 400 microns thick. Next, workers install the windows. Each one tips the scales at 74 kilos. Then they glue down the cushioned floor, one board at a time. Meanwhile, cablers prepare the wired infrastructure of the AGV train.
I run cables with the help of a laser. Here, there is a little circle that shows me the beginning of the cable. And then I follow the path. It's a bit like a puzzle.
From beginning to end, she follows the prescribed path to prepare over 1,000 cables for installation in the AGV shell. This is like the central nervous system of the AGV body, carrying electrical signals from the brain to the heart and limbs. The cables are bundled in harnesses, which will be then installed directly into the shell. A special conveyor is used to install the harnesses along the ceiling. Next, the train gets a state-of-the-art driver's desk. But a new driver's cabin means new obstacles.
Because the AGV is a new train, obviously it's a new environment. So one of the things we have to do is develop new tools.
They decided to save installation time by pre-assembling the desk and wheeling it in on a custom-built cart. But the devil is in the detail. All the handcrafted and carefully calibrated equipment is useless if the desk doesn't fit through the door. Once through, there's another problem. They now have to turn the desk in a space smaller than your average walk-in wardrobe. And it's not getting any lighter. Problems like these can delay the entire production line, jeopardizing on-time delivery of the train. The workers have to finish the job the only way they can, by hand.
We had some problems. Now we'll have to adjust a little bit. We have to make some modifications to the equipment now, and I think after that, it'll be good for us.
Train building is more than just high-tech automation. It also takes a lot of perspiration. Last but certainly not least, it's time to tie together 3 factories of work in what the train makers call the marriage. The finished AGV bogie is towed to the main assembly hall, which they appropriately call the cathedral. The heart and spine of the AGV is ready for its nuptials with the body of the train. It's a match made in high-speed heaven. But before any new AGVs are taken out for a ride, they go through a barrage of static tests.
Here, we verify if everything works on our trains. There are 7,000 test points, divided into 28 principal functions.
They check everything, from the pantograph above to the electrical connections below. All in all, the tests take 1,200 hours for each train. That's 50 days of testing before the train moves a single kilometre.
Finding anomalies and failures and fixing them isn't easy and can take a very long time, sometimes up to several days. It's a very rewarding and interesting part of the job, even though we'd like for it not to exist.
After weeks of static tests, it's time to see if the AGV coming off the line at La Rochelle can move. This happens on the 2-kilometre track at Alstom's main test site at Bellevue, just down the road from the factory. With 30 million euros on the line, the first test run of a new AGV is an extremely tense moment.
There are always fears, but when we put all this equipment together in operation, it does not always go as planned.
The moment of truth. testing team stands by. And it's off. From 0 to 60, the train is performing just as predicted. But a 60-kilometre-per-hour run is just the warm-up. The train is now ready for the high-speed main event. On to Italy. The high-speed testing crew on the AGV has been pulling the night shift for over 6 months. And testing all night long on a mobile lab creates its own set of needs.
Because we are living in this train like in a submarine, as we have to be autonomous, because it's very rare that we are in the same place. And we are always traveling in different places, so we have to be really just to be able to count on our own. We have as well a little Frigidaire. We have the emergency kit, water reserve. We don't have free access to water sometimes, so we have all the possible tools that is used on the train. We have the power room, which is just dedicated to the instrumentation of the train. This is a group electrogen that is generating 220 volts, the common one, just to supply all equipments. So basically, this baby is running most of the time, about 15 hours a day. So it's becoming a friend of us, can say this. And here we have the tanks for the gasoil, 30 liters a night.
And of course, lots and lots of coffee.
Not too bad. Sorry, I got a problem there. I have to go, by the way.
There's a problem, and Guillaume springs to action. The train has stopped and every engineer on board checks their systems. The pantograph fell away from the power line, causing a power cut-off.
Le TCMS aux commandes. The train control system is at the moment trying to see what's the problem we are having in the cabin.
At this hour, any problem can raise tensions.
Fabio, che cosa facciamo? Tranquillo sì, però vedi che siamo 25 persone qua e...
Facciamo 4 lotti. L'altra volta non è successo.
Non lo so che siamo troppi, però...
L'altra volta non è successo.
Non lo so, però...
Tranquillo Guillaume, non ti preoccupare.
Mi preoccupo un po' perché...
No, non la sbagliamo, non ti preoccupare.
They can't risk another malfunction.
Siamo pronti, signori? Un attimo, che abbiamo già un'oretta e mezzo di ritardo.
The team switches to the backup pantograph for the next run. After 3 more test runs, the night is finally over.
We're approximately 5:30 and we are at the end of the night. We did perform the 5 tests that was planned. We get little issues, but as usual, but we had to face it and we did face it. The test went pretty well. We did succeed 4 tests over the 5. And the results were really good, so we are really happy. A little bit tired, but happy. Yeah, today is a plus, definitely it's a plus. It's always a plus, comunque. Però è stato... I am speaking Italiano. Bene, bene. No, it was a very nice night, and we're ready for the next one tomorrow. Same time, same place, to do it again.
Over 10 years in the making, the Alstom AGV is ready to zoom through the Italian countryside. Who knows what advancements the next generation of trains will bring? But until then, the AGV stands as the most advanced train to come out of the Alstom mega factory.